In this session, we're going to see what properties of logarithms are. They are also called laws of logarithms. Recall that if you have a multiplication of, say, x cubed times x to the fourth, that we add the exponents. It becomes x to the 3 plus 4, right? So when we multiply results, we end up adding exponents. Also, if you have a division of, say, x to the 9th divided by x to the 6th, that becomes x to the 9 minus 6. That is to say that if we divide results, we end up subtracting exponents. Things like these are the basis of our properties or laws of logarithms, which I'm going to write down in general and enumerate, and then we will use throughout this video. Based on what we just saw, we can say, hence, the log base b of m times n is equal to the log base b of m plus the log base b of n. Now, what does this have to do with what we just saw? Well, when we multiply results, we add exponents. Because remember, a logarithm is an exponent. I'll call that property 1. Property 2 states that if we have a quotient, log base b of m divided by n, then that, can you guess, is going to be the log base b of m minus the log base b of n. And this should again make sense because when we divide results, we subtract exponents. If we use 1 over and over again, that is the one where you're adding because you have a product, then log base b of m to the r could be thought of as repeated multiplication. And the property is that the r comes out in front. And so log base b of m to the r is r times log base b of m. You see, the repeated multiplication that m to the r represents becomes now repeated addition, which results in the exponent becoming a coefficient. Those are kind of the biggies, but there are still more. What I'm going to call property 4, and these are not really in any particular order. The log base b of b to the r is equal to r. And what I'll call 5 is that b to the log base b of r is equal to r. These I'm going to call cancellation or inverse properties. Just as in the case that addition undoes subtraction and multiplication undoes division, exponentiation undoes a logarithm. And that is a two-way street. What I will call property number 6 is log base b of b is equal to 1. The exponent that gives you the base that you started with is a 1. And number 7, log base b of 1 is equal to 0. Because 0 is the exponent that gives a base a value of 1. Leave space on your paper for one more. To finish all this off, there's something called the change of base formula, and we'll get to that later. First, I want to show you how these properties work. For our first batch of examples, we're going to use the properties or laws of logarithms to find the exact value of particular expressions without using a calculator. First, we're looking at log base 2 of 2 to the negative 13. There are like two ways we can look at this. One of them is that the bases match, and so we have a cancellation property that says we can do away with the log and the exponential, and that the answer should be the exponent, negative 13. The other way we could look at this is to bring the exponent, negative 13, out front. And now we have negative 13 times the log base 2 of 2. The log base 2 of 2 is 1. So negative 13 times 1 gives us negative 13. Either way, we get the answer of negative 13. Next, we have log base 6 of 9 plus log base 6 of 4. I have a sum of logs with matching bases. That's key, by the way. In the previous slide, when we were looking at log base b of m and log base b of n, it was very important that they were the same bases. Well, since these have the same base, we have a property that says that a sum of logarithms becomes a product. And so we're looking at log base 6 of 9 times 4. And notice the base is still 6. Now, inside the parentheses, log base 6 is 36. 9 times 4. And that you can do in your head. Log base 6 of 36, the exponent on 6 that gives 36 is 2. And there it is. Next, we're looking at 5 to the log base 5 of 6 plus the log base 5 of 7. First, what I want you to do is apply a property that you know to the exponent, and then see if you can finish this off. So pause the video and do that. So combining the sum that's in the exponent, I get 5 to the log base 5 of 42. But now 5 to the log base 5 of anything is the thing, right? We have that cancellation property since the bases match. So the answer here is 42. Next, we're told to represent natural log of 2 with a and natural log of 3 using b. And then to use properties of logarithms to write given expressions in terms of a and b. In other words, we need to envision how we can express what we've got as either natural log of 2 or natural log of 3 or some combination thereof, and then replace those by the letters a and b. First, we are looking at the natural log of 1/2. As it happens, 1/2 is 2 to the negative 1. And so the natural log of 1/2 is the same thing as the natural log of 2 to the negative 1. Now I have an exponent in a logarithmic expression. The exponent can come out front. And so this is the same thing as having negative 1, if you like, times the natural log of 2. But then the natural log of 2, we are told, is represented using a. And so the answer is negative a. And this is what is meant by writing the expression in terms of a and or b. Next, we have natural log of the 5th root of 6. First off, that root can be written as an exponent. So this is natural log of 6 to the 1/5. Now the exponent comes out front using that property of logarithms. And so this becomes 1/5 times the natural log of 6. Now what I'd like to do is write 6 in terms of 2 and 3 because that's what we were looking at, right? Natural log of 2, natural log of 3. As it happens, 6 is 2 times 3. So we have 1/5 times the natural log of 2 times 3. Enter a property of logarithms that applies to a product inside of a log. This becomes 1/5 times the natural log of 2 plus the natural log of 3, but we have to remember that the 1/5 applied to the whole thing, and so the natural log of 2 plus the natural log of 3 should appear in parentheses. Now we were told to represent the natural log of 2 using a and the natural log of 3 using b. And so we end up with 1/5 times the quantity of a plus b. You could distribute the 1/5 if you wanted to. Next, we're given various logarithmic expressions, and we are told to use the properties of logarithms to expand them. What that means is write them using pluses and minuses, turn them into terms. First, we have log of a squared over b to the 4th times the square root of c. The first thing I note is that we have a quotient, and the quotient will turn into subtraction. So the first step I'm going to write is log of a squared minus the log of the denominator, b to the 4th times the square root of c. And then I noticed that with the b to the fourth times the square root of c, that's a product. And so I'm going to write that portion as log of b to the fourth plus the log of the square root of c. There was a minus in front of that one. There should be a minus in front of both of these. And so I'm going to put those into parentheses. Nothing has happened so far with the log of a squared. So what we have is log of a squared minus the quantity of log of b to the fourth plus log of the square root of c. Now it's time to deal with the exponents. A squared, that 2 is going to come out front. B to the fourth, that 4 is going to come out front. And the square root of c, we need to envision that as an exponent of 1/2. It is also going to come out front. Furthermore, we need to distribute a negative. I think I've gotten that a little messy, but hopefully we'll see what's going on here. 2 times the log of a minus 4 times the log of b minus, because we distributed that negative, 1/2 times the log of c. And so you see the portion that was in the denominator to begin with, b to the fourth times the square root of c, each of those terms has a minus in front of it, indicating that that was associated with the denominator. And all the exponents are out front. We've expanded this as much as we can, and this is the answer. You may be wondering why. This is a process that would be useful, required in calculus. I know, whatever, whether you're going to take calculus or not. This is just part of you understanding the language of logarithms. Isn't that fun? Next, same instructions. The natural log of 3x squared divided by x plus 1 to the 10th power. Go ahead and pause the video and see if you can expand this expression. So for my first step, I have recognized that we have a quotient and written that as a difference, natural log of 3x squared minus natural log of x plus 1 to the 10th power. Well, the natural log of 3x squared is now a product, right? That was the numerator of the quotient, was a product. And so we have the natural log of 3 plus the natural log of x squared minus the natural log of x plus 1 to the 10th power. Now, each of the exponents that we see, i.e. x squared, x plus 1 to the 10th power, comes out front as a coefficient. And so we have the natural log of 3 plus 2 times the natural log of x minus 10 times the natural log of x plus 1. Now, some books will put that natural log of 3 in parentheses. I don't care. They might put 2 times the natural log of x. They'll put the x in parentheses. I don't care. The natural log of x plus 1 absolutely has to be in parentheses because those are two terms. So it's about whether you have one or two terms, essentially. Furthermore, a lot of people will mess up. They'll take the natural log of x plus 1 and turn it into something different. There's nothing you can do with this. We have no property dealing with a sum inside. Go double check it. You have a property dealing with a product inside that becomes a sum. You don't have a property dealing with a sum inside. This one's done. Last but not least for this set of examples, the log base 2 of x cubed times the square root of x minus 1, all divided by 3x plus 4. See what you can do to expand this logarithm. Go ahead and pause the video. Okay, so I've written this as log base 2 of x cubed times the square root of x minus 1 minus the log base 2 of 3x plus 4. That x cubed times the square root of x minus 1 is a product, and so I'll write that as the log base 2 of x cubed plus, I'm going to go ahead and think ahead here, log base 2 of x minus 1 to the 1/2 power. And then finish it off by saying minus log base 2 of 3x plus 4 If I can squeeze that in there. Good. Now I have a couple of exponents. Log base 2 of x cubed. That 3 should come out front. Log base 2 of x minus 1 to the 1/2. The 1/2 should come out front. And so my final answer is 3 times the log base 2 of x plus 1/2 times the log base 2 of x minus 1 minus log base 2 of 3x plus 4. This is the final answer. Remember, I cannot break up a sum inside of a log or a difference inside of a log. Furthermore, we were off the hook for the previous two examples. The first one was log base 10, and so it was just log. Second one was natural log, so we wrote ln. This one is log base 2. We need to remember that every logarithm that we write as a result of this is going to have a base of 2. Next, we're asked to perform that process in reverse. Use properties or laws of logarithms to combine logarithmic expressions. And first we have the natural log of 2 minus the natural log of 7 plus the natural log of 5 minus the natural log of 3. Here's the deal. Terms that are positive are going to end up in a numerator. Terms that are negative are going to end up in a denominator. And so this is going to become the natural log of 2 times 5 in a numerator divided by 7 times 3 in the denominator. And so ultimately this is the natural log of 10 divided by 21. Next, 1/2 times the quantity of the log of x plus the log of y, and then minus the log of z. Using the order of operations, I can simplify the brackets containing log x plus log y. And so I will do so by applying the property of logs that applies to a sum. And write down that we have 1/2 times the log of x times y minus the log of z, which has been unaffected so far. Now we have a coefficient of 1/2. That becomes an exponent on xy. You see, it doesn't apply to the z because the z wasn't wrapped up in that quantity to begin with. I'm going to express that as the log of the square root of x times y. And then we still have minus the log of z, which we're now ready to deal with. Terms that are positive end up in a numerator. Terms that are negative end up in a denominator. And so this is going to equal the log of the square root of xy divided by z. Parentheses around that argument, as far as I'm concerned, are optional. It's just one fraction, right? So no confusion there. Next, we have 1/2 times the log base 3 of x plus 3 times the log base 3 of the quantity of x minus 1. Notice the parentheses there. First thing I notice is that the bases of the logs match. That's essential. We didn't really think about it in the other two examples. We had first a natural log and then a base 10 log. But here we have a log base 3, and we note that those bases match. Next, I notice that we have coefficients. 1/2 for the first term, 3 for the second term. Those are going to become exponents as before. And then I notice that we have a plus, and so this is going to become a product of inside of the log. So I'm going to write this down as log base 3 of the square root of x times the quantity of x minus 1 cubed. You may see this with a bracket in the argument. Probably good form to use it, though since it's only one term, I would say not essential. And there we are. We now turn our attention to the change of base formula. Change of base formula is useful if you need to express, say, the log base 2 of, say, 17 or something like that, where there's not an exponent on 2 that you can think of that would give you 17. It's not a rational number. And so you might just need a decimal approximation for it. And as it turns out, log base 2 of 17 can be done in the calculator provided we change the base. Right now the base is 2. The change of base formula itself says that the log base b of m is equal to a quotient of the log base a of m in the numerator and the log base a of b in the denominator. Notice that this is different than what we looked at earlier, say log base b of m divided by n. That is just a log with a quotient inside of it. This is a quotient of logs, right? The log is written twice. On that note, I'm going to go back and talk about a common pitfall. In the previous slide, our instructions were to combine each expression. Sometimes, and often on a test, I will put write as a single logarithm. Folks, if I tell you to write something as a single logarithm, then you write ln or log only one time in your answer. You write it more than once, that's not a single log, that's not even following the directions. Okay, back to where we were. Log base b of m is equal to log base a of m over log base a of b. This is confusing, it's hard to remember. Here's the deal. The number that's written kind of big, the result m, goes in the numerator of the fraction. The one that's little, log base b, becomes the argument in the denominator of the fraction. What about a? A is any base that is allowed, so it has to be bigger than 0, but we don't allow a base of 1, as you recall. What matters is that the a's match. Since we're going to typically be using our calculators for this, it would be useful to write either log or ln. Use a base of 10 or a base of e. I personally more often use the natural log. The reason? It's easier for me to write than log. A lot of times when I write log, it looks like lug. And now we're going to use a calculator in the change of base formula to find the values of particular logarithms. To 4 decimal places, it says. And pay attention to those instructions too. Log base 1.2 of 13.7. So let's glance back at our change of base formula. The argument 13.7 is something that ends up in the numerator. The base of 1.2 is something that ends up in a denominator. And when we change the base, we can change it to any base we want, provided that they match. Because I'm going to use the calculator, we want to use either the natural log or the common log. For this first example, I suppose I'll use the common log, and so log of 13.7 divided by the log of 1.2. I know the bases match because I wrote log both times, and that base is 10. Putting this into the calculator gives me approximately 14.3559. So now you have a way of getting a calculator answer for something with a, we'll call it a non-standard base. Next, log base 1/4 of 3. Again, the argument 3 is going to land in a numerator somewhere. The base of 1/4 is going to land in a denominator somewhere, and I'm actually going to call that 0.25 because it's less likely to mess me up with my calculator. I can change the base to any base I want, provided they match. This time I'm going to use the natural log. So log base 1/4 of 3 is the same thing as natural log of 3 divided by the natural log of 0.25, which my calculator tells me is about negative 0.7925. And that's that. If you had written this, by the way, and it would have been fine, as natural log of 3 divided by the natural log of 1/4, that's fine. You just have to make sure that your calculator knows that the 1/4 is in the logarithm. And so you'd have to do natural log of parentheses 1 divided by 4 for that base of 1/4. Our last example for this session, solve an equation accurate to 4 decimal places, and our equation is 0.56 to the x is equal to 8. Well, the first thing I'm thinking is we can convert this into a logarithmic expression. And so I'm going to write down log, and what's the base? 0.56 of 8 is equal to x. Now, I don't know log base 0.56 of 8, but I do have a change of base formula. And so x is going to equal, and I told you I typically will use the natural log, of 8 divided by the natural log of 0.56. We're told accurate to 4 decimal places, and so my calculator tells me that x is approximately negative 3.5864.